This visualization displays a dense, two-dimensional vector field. A vector field is a space where every point has an assigned magnitude and direction, often used to model physical phenomena like fluid velocity or electromagnetic forces. If we drop a closed, one-dimensional boundary loop into this fluid, a distinct computational problem emerges. How do we calculate the exact circulation of the field along this specific path? Typically, you would compute a line integral piece by piece. A line integral is a mathematical operation that sums up the total effect of a field along a specific curve. In applied engineering and physics, brute forcing a line integral around a complex, multi-segmented boundary requires an immense amount of time and processing power. This topological equivalence solves the problem. Total circulation along the boundary strictly equals the sum of microscopic rotations inside the enclosed region. This anchors our thesis. The boundary integral equals the interior integral. We will trace the exact mathematics of this equivalence. We begin with Green's theorem in two-dimensional planes, scale the logic up to Stokes' theorem for three-dimensional surfaces, and finally arrive at Gauss's theorem. These three theorems represent a single, scalable geometric principle. They serve as a highly efficient computational bypass for otherwise impossible integrals. We can test this bypass using a specific scenario. Consider evaluating a continuous vector field, defined mathematically as f equals x plus yi plus 2y plus xj around a distinct square boundary. Tracing the perimeter from the origin 0, 0 up to the coordinates kk requires the standard brute force method. The boundary must be broken down into 4 distinct directed segments. That requires 4 entirely separate parameterizations to complete the calculation. This equation is Green's theorem, providing a direct bypass. Instead of tracing the edge, we take the partial derivatives of components p and q to extract the scalar curl, a single value representing the exact amount of microscopic rotation at a specific point. Executing this operation collapses the tedious 4-part path integral into a single trivial double integral, evaluated neatly from 0 to k. Green's theorem effectively transforms a complex geometric problem of path tracing into an algebraic problem of area evaluation. This approach encounters friction when the boundary is defined by curves, where standard Cartesian limits become incredibly difficult to track. This schematic displays a region bounded by 2 concentric semicircles. Attempting a standard line integral here forces you to awkwardly switch between linear segments on the x-axis and circular parametrizations for the sweeping arcs. Applying Green's theorem allows us to extract the internal curl of the field, yielding the algebraic expression y minus 2x. Integrating this new expression over a circular region means we must abandon the Cartesian grid entirely and switch to polar coordinates. This notation shows the strict rule of dimensional scaling during coordinate transformations. You must include the Jacobian determinant. The Jacobian determinant is a mathematical scaling factor, ensuring areas are measured correctly when translating from one coordinate system to another. By combining Green's theorem with the polar Jacobian, a multi-segmented curved boundary is reduced to a straightforward polynomial evaluation. What happens when our domain is no longer a flat plane, but a curved surface floating in 3-dimensional space? We apply Stokes' theorem, the direct 3-dimensional evolution of Green's theorem. The one-dimensional line now acts as the boundary for a 3-dimensional surface area. This matrix outlines the necessary mathematical upgrade. The 2-dimensional scalar curl is no longer sufficient, so we calculate the 3-dimensional curl vector using a cross product. A cross product produces a third vector strictly perpendicular to both. Consider a specific geometric problem, a cylinder defined as z equals x squared plus y squared, sharply cut off by the plane z equals 10. Here we see the 3D wireframe of that exact geometry. To equate the boundary line to the surface itself, the curl vector is mathematically dotted with the surface's normal vector, a directional arrow pointing exactly perpendicular to a specific point on the surface. The mechanical steps require parametrizing the surface using polar coordinates, and then computing that normal vector via the cross product of the partial derivatives. Stokes' theorem relies on the exact same logic as Green's. Interior spin equals boundary flow. It simply incorporates vector cross products to manage the depth of the z-axis. There is a highly specific geometrical case to consider. What happens to our double integral if the internal rotation, or curl, of the vector field is exactly 0? This split screen compares two fields. On the left, a field with clear local rotation. On the right, a radial field where vectors flow outward with zero spin. If the partial derivatives match, the scalar curl is zero, making the interior double integral equal zero. If the closed loop integral is zero, the field is defined as conservative. A conservative field is an environment where the energy required to move between 2 points depends only on the start and end positions, making it completely independent of the path taken. This mathematical dimensional escalation continues well beyond simple surfaces. This fluid simulation introduces Gauss's divergence theorem. Just as Stokes maps a one-dimensional boundary to a two-dimensional surface, Gauss maps a two-dimensional closed shell to the three-dimensional solid volume it encloses. Whether you are calculating across 2, 3, or infinite dimensions, calculus maintains one strict rule. The invisible behavior of the interior is perfectly and undeniably encoded on the boundary.